Suppose that the absolute value of a is less than 1. Let's prove these two infinite series are correct. The way that we're going to do this is by appealing to de Moivre's theorem. So let z be equal to a times cosine theta plus I sine theta. Then z to the nth power would be equal to a to the n times cosine n theta plus I sine n theta. And to be more explicit about it, let me write it like this: a to the n times cosine n theta plus I sine, or I times a to the n times sine n theta. Now you'll notice that these are the terms that appear in the series on the right-hand side. If n equals 0, then we have a to the 0, which is 1, times the cosine of 0, which is 1, so that's the 1 term. If n equals 1, we have a cosine 1 theta, then a squared cosine 2 theta, a cubed cosine 3 theta, letting n go from 0 to infinity. Likewise, the imaginary part, if I let n equals 0, I get 1 times the sine of 0, which is 0, a to the first times sine of theta, then a squared sine 2 theta, a cubed sine 3 theta, and so on. So these two terms are the real and imaginary parts, form the real imaginary parts of z to the n. So the series, the top series, is the real part when I take the sum from n equals 0 to infinity of z to the n. And likewise, the imaginary part is the second series. So somehow we have to evaluate the series. Well, by the since the modulus of z is equal to a, and that is less than 1, or I should say the absolute value of a, because a itself could be negative. Since the absolute value of z is equal to the absolute value of a, which is less than 1, we know that the series converges. And so by the formula for a geometric series, this is equal to 1 over 1 minus z. The first term over 1 minus the common ratio. Okay, now let's figure out the real and imaginary parts of this. So that's 1 minus a cosine theta plus ai sine theta. So to get the real and imaginary parts, we'll write this as 1 minus a cosine theta plus I times a sine theta all over 1. And now let's multiply by the conjugate so that the imaginary part gets out of the denominator. So that's 1 minus a cosine theta minus I times a sine theta. So that goes in the denominator. And the exact same thing goes in the numerator. So I'll just copy it. Let's try to copy it. And the exact same thing goes in the numerator. So on the top, we have the expression we just said, 1 minus a cosine theta minus ia sine theta. In the bottom, we have the square of the first term, 1 minus 2a cosine theta plus a squared cosine squared theta minus the square of the second term, so I squared sine squared theta, or times a squared. A squared, I squared, sine squared theta. Okay, so the denominator is going to be equal to 1 minus 2a cosine theta plus a squared, because we have a squared cosine squared theta plus a squared sine squared theta becomes a squared times 1, which becomes a squared. The real part is 1 minus a cosine theta plus I times, and I realize I made a mistake, so rather than redoing this whole video, the mistake is that this should have been a minus here, whereas this should have been a plus. So plus I times a sine theta over 1 minus 2a cosine theta plus a squared. And so the real part is going to be the sum of these terms, 1 plus a cosine theta and so on. The imaginary part will be the sum of the a sine theta plus a squared sine 2 theta, a cubed sine 3 theta, and so on. And so we've actually proven two series at once using the formula for the infinite geometric series.